we are now moving to our last speakers. It's a great pleasure that I have to introduce Marcus Cruz and Brenda Parker. Marcus Cruz is an architect and professor of innovative environments at the Bartlett at the University College of London, and his main research focuses on bio-integrated design in buildings. And Brenda Parker is not an architect, he's an associate professor in sustainable bioprocess design at the Department of Biochemical Engineering, also at the University College of London. And together they run the BioID, a multidisciplinary research platform and a master program that investigates design that is driven by advances in biotechnology, computation, materials, and fabrication. So please help me welcome Marcus and Brenda to the floor. Thank you.
Thank you, and thank you for the warm welcome. And what we'd like to do today is really share our thoughts on how we believe the responsive city is really a photosynthetic city, and share the work of our interdisciplinary research platform at UCL, where we combine biochemical engineering and architecture and really look at nature as the medium in which we work in. So what do we mean when we say that we believe that photosynthesis is the ultimate responsive system? It's regenerative, taking simple inputs of sunlight, carbon dioxide and water, and using photosynthesis as a way of building from the bottom up, thinking about the primary producers within our environment, organisms such as cyanobacteria, who can fix nitrogen from the atmosphere and photosynthesize. And these also form the basis of many of our ecosystems. And yeah, for our design processes, what does it mean when we start to work from the bottom up? And how might we transform our cities into photosynthetic cities?
So we are really keen on thinking a bit beyond the Anthropocene, and to think of what could be the vision of how we're going to design our future human habitat. We are convinced that a lot of people are talking about things, talking about all the dramas and tragedies that are going to face us, but very few are actually really starting to create a scenario of what might come, what we might be achieving in the post-Anthropocene era. And what we have been coining, as some others, as a sort of the Bioscene era that we are engaging with. Now, we need a new language in architecture. We need profoundly to change how we design, bring computational tools together with biotechnological tools together, and really with new materials, new systems, create qualities that we haven't actually had before. And that excites us. That gives us a sense that there's something that is a great opportunity to engage with.
And so perhaps a good example is our vision of engineered living materials, working with organisms like Oscillatoria to really understand how, through biological mechanisms, we can catalyze precipitation of carbon dioxide into calcium carbonate, biomineralizing structures. But what does it mean when we design with such decentralized systems? And here is really some examples of the work from Prantar Tamuli, one of our students. We've just applied for a patent for this technology, really because it's the intersection between both the biological agenda and material development, as well as fabrication, to be able to produce these kind of substantial materials with interesting properties for architecture, but also novel properties as well, such as regenerative structures that are capable of sustaining their own growth. I'm moving from the bulk to the veneer because biology loves the surface area, and this is the work of Nina Jitanovic, who's another member of the BioID team, and she has been looking at this idea of biogenic crusts, how we can use microorganisms to precipitate silica, to produce lustrous environments, to look at the idea of perception in biology, to move beyond perhaps very simplistic ideas of growing organisms on surfaces, and to really go beyond and think about how these perceptual qualities can also be linked to global nutrient cycles. So how can we intersect with global carbon, nitrogen, calcium, silica cycles as well within our built environment? And what would that mean for our future cities?
Nina Jitanovic, who was actually a student at IAAC before, and this is quite fascinating to see how the crossover of knowledge comes from one school into another, etc., and now works in an environment where we both, biochemical engineers and architects, got together to really create something completely new.
So Nina works a lot with ceramics, and another project looking at a kind of different aspect of ceramics and producing a functionalized structure is the Indus project of Shanil Malik, another one of our PhD students, where we had embedded algae-laden hydrogels into the ceramic scaffold with the idea of performing bioremediation, so using microalgae to take up pollutants from wastewater. This project was also looking at perhaps narratives around decentralized manufacture in other countries as well, so looking at perhaps non-urban contexts, but actually that of artisan manufacturers. This is a demonstrator that we built for London Design Festival. And again, this idea of being able to explore through making and scaling up, and not to be afraid of scaling up or scaling out when it comes to biology. And in this particular project, it really taps into the idea of water being such an essential component of all of designing with life, designing with biology, and to be able to regenerate water for reuse. And within our urban centres, we have such a density of wastewater production. It's perhaps an interesting concept to explore it within our built environment. Now, a material we use quite a lot is hydrogel. It was a component of the Indus project indeed, but it's the idea of creating a localized environment of water intensity to be able to support biological growth. Now, obviously, working with hydrogels poses some interesting challenges. They're not structural materials. They sustain life in a really interesting way, but they also require their own considerations in terms of manufacturing, in terms of fabrication, and in terms of design. And it's really working within this intersection of all of these worlds. We find the beauty and the challenge of biointegrated design, but it may force us to question exactly some of the things that are maybe taken as a given, that all materials within architecture should be structural or load-bearing. In this case, they're absolutely not.
We have also looked at the materials we have produced and the waste that this has created, especially as designers. And currently in London, there's a very important exhibition going on called Waste Age at the Design Museum. And it's really an opportunity to look at what we as designers have actually contributed to the world of waste and how we might make use of this in new systems, new construction processes. So we build this wall, which we call the calcareous arabesque, which is a prototype for an acoustic and thermal wall that we might want to bring then outside at some point. And it's made out of material that results from a byproduct of the sugar refinement process. The large quantities of calcium carbonate and other things that are just simply thrown away that we turned into a composite. Now, we have seen a lot of walls, and for us, surface area is really important. And if you think just for a moment of how much new surface area we humans have contributed to our world's surface, it's staggering. You just take a city like London and take all the facades and flatten them out, and the footprint of London will be probably around 15 times bigger than what the city currently embraces. If you take the sprawling cities and consider that our world-built environment is going to double up in the next 30 to 40 years, as it's predicted, the amount of surface area will be absolutely extraordinary. So we actually looked at some of the facades a bit more in detail and started sort of questioning how much surface area does actually a little building have more than its footprint? And guess what? A little sort of Victorian terrace house has around 3.24 times the size of a footprint. That's not counting obviously all the ornamentation and all this sort of crevices that exist around windows, etc., that are great opportunities for growth. But when you go to large-scale skyscrapers, like the Shard in London, the surface area is 18.6 times bigger than its footprint. Now, this is an opportunity. This really creates a phenomenal chance for us to use these facades as interfaces to engage in a future bioresponsive manner. So one of the phenomena we look at was poikilohydry. Now, this is a phenomenon of some species who are capable to switch on and off their photosynthetic activity. So we have built these moss walls, not because we like so much moss itself, it's because mosses, as cryptogams by and large, are really capable of doing exactly that, to be poikilohydric. Not to wait for water, so they don't get destroyed, they don't get, or they get dormant, and they wait for moisture to be photosynthetic again. So we start thinking that maybe what we need is a poikilohydric design system in our cities. And that is that these huge amounts of surface areas can be biocolonized and be self-regulated. So this was one of the first walls we built at the St. Anne's schools in South London, where we transplanted moss onto it, and we are monitoring these walls now for a few years. The other thing really is that if we want to make a change, we need to start thinking about our cities as being photosynthetic cities, to go back to photosynthesis as such basic, decentralized, powerful, high-tech system, and bring it into designs that we haven't seen before, which are ever-changing. They wouldn't look ever the same in the summer or in the winter, and they will be great ecological opportunities. And here we have a very small movie just to show you, one of the possible scenarios.
Yeah, so if we wish to really grow our cities, I think this is a topic that we have touched on in some of the talks today. What might that mean in future? So this project looks at the idea of using plant callus tissue, this is undifferentiated plant tissue, to be able to grow structures, ab initio, to be able to design them from scratch.
Do you mind making the sound a bit higher?
We're going to depart the magical world of the digital and perhaps bring you back into a provocation to kind of finish off with. So what if biology is not always compliant with what we want it to do? And we're more and more interested in the idea of the heterogeneous, of the indeterminate state of the biofilm as an emergent property. This isn't always pleasing for us to look at. And we also have this difficulty of transitioning from the monoculture, this purity of the laboratory environment, into the outdoor state where things are more complicated, more difficult to control. And we may have these intermediate phases, which, again, how can we design for and how can we accommodate biology into those when, in actual fact, we may have periods of dormancy and growth and regrowth?
Ultimately, what we think, and that's the last sort of statement, is that we need to start designing for aging buildings. We need really to shift radically from the idea that what we design is new and will stay new. It will not. It will be biocolonized, it will age. And the question really is whether we are ready to relinquish our control over nature and let it actually do what it does with what we design and how we interfere. Are we really? Here are a few just references that might be helpful for some of the discussions. And thank you very much.
Thank you.